My name's Larry Horry. I've been a vibration specialist here at Martin Engineering for about 14 years. In my role, I help solve material flow issues with properly sized and applied vibration products using the basic principles of applied vibration. So we'll get started here. We're going to talk today about the most common issues associated with bulk material flow through bins, hoppers, and chutes. Some of those are rat holing of material, clinging, bridging, and arching. And we'll also discuss some of the variations in material characteristics that contribute to those problems. And then we'll talk about how we optimize the material flow using properly sized and applied vibration products. One of the most common material flow issues that we see is rat holing, which is pretty commonly viewed out in the workplace, where material builds upon the walls and creates narrow passages for material to flow. This reduces the throughput, the volume, and leaves material behind that can stagnate or spoil. There are some bin hopper design principles that can be used to help alleviate that, including larger diameter or larger discharges. But we're going to focus on how to deal with these issues as they come and not in hopper design. Clinging material, simply, it's just material that hangs on the sides. Usually it's going to be fine powders with high moisture content, sticky particles, those sort of things. Hopper design also with maybe not enough angle, particularly for the material. And then environmental factors like fluctuating temperatures and humidity that can contribute to this. Bridging or arching, very common. Material flow issues, that's just where the material packs above the discharge due to the weight of the material and just won't let anything flow. Typically with properly sized and applied vibration, we can break loose one of the legs of that arch or bridge. And once we do that, then we can collapse the rest of the material on top of it. The variations in material characteristics that we talk about are particle size, the shape. Irregular particles create more friction as opposed to spherical particles. Moisture content's huge in this. We'll talk a little bit about how we deal with that. Temperature is an issue often. Cold temperatures and high moisture content don't mix well when trying to move material through bins, hoppers, and chutes. And then chemical composition, additives, can inhibit the flow characteristics. We'll look at a photo here of a large hopper in a seed corn plant, which is interesting in that you can see on the lower level all of the pink hammer rash, which we'll look at a little more in depth. This was simply an area where the operator could lean over a railing with a dead blow hammer and hit that hopper to break loose that material. Now, seed corn generally flows very freely, but it's that chemical additive of the insecticide, fungicide that they add to it. And as it sits in that hopper for a period of time, that hardens. And they open that gate, nothing comes out. They have to break that loose. So we applied, as you can see in there, a pretty large piston vibrator to replace the operator from having to lean over the railing to knock loose that material. So some common methods of dealing with material flow issues. This is not all inclusive. There's probably some more out there, but when I'm in plants, we're talking about people who are using air or water lances to break loose material. Silo clean out equipment, which can be expensive and sometimes not readily available when you need it. Explosives, which are inherently dangerous, create hopper damage as well. And then the old reliable sledgehammer. I call that still today our largest or our biggest competitor is the sledgehammer out in the field. Regarding sledgehammers, there's no data available out there right now on the specific number of injuries that are caused from dealing with those, but it's reasonable to believe that there is a significant number. I was in a plant, last year it was, in a coal-fired power plant where they had two shoulder injuries recently due to guys having to swing sledgehammers. And we found that by placing a properly sized and applied vibrator to replace that hammer, that they eliminated the need for the operator and thus reduced the risk of injury. And here's a couple photos of what can happen to the structure when using a sledgehammer. You can see in the cone photo in the top right, they've caved that whole cone in from beating on it with a hammer. And then on the lower left, you see all of those dimples that are created in the side of that wall where they've been hitting it. Each one of those dents on the inside of that hopper creates a shelf for material to build up upon. So it just really even just enhances the issues that they're experiencing. So, how can vibrators help with this whole process of the rat holing, bridging, clinging, arching, material characteristics of high moisture, chemical additives? Here's how they can help. They can stimulate the continued flow of materials, significantly reduce the potential damage to the structures, and then those other methods of intervention, like swinging the hammer and what have you, can be costly and unsafe. When we're working with vibration products, one of the first questions that we ask, or the first piece of information that we get, is how would you like to power this vibrator? Most times it's going to be simply what's available in the area that they're trying to address. And those power sources are either electricity, compressed air, and in some cases, hydraulic fluid. We'll talk about each of those as we look forward. For electricity, simply they're available in a variety of voltages, including 12 and 24 volt DC. They're not susceptible to issues associated with frozen air lines, like we'll talk about with the compressed air powered vibrators. They're available in different speeds, and we'll talk about how we use the different speeds for different materials. And then they have an ambient temperature rate range from 22 degrees to 104 degrees Fahrenheit. Electric vibrators generally cost more off the shelf initially than pneumatic vibrators. When we're looking at compressed air, there are some issues with them, but there's also some real virtue to them. They cost less off the shelf compared to the electric vibrators, but they'll cost more to operate over time just due to the power consumption of the air compressor that produces the compressed air to operate. There are some ROIs that can be filled out and provided, changing from pneumatically powered vibrators to electrics over time. We can power both linear and rotary vibrators with compressed air. We'll talk about the differences between those style vibrators. And in cold weather, as we discussed earlier, they can be problematic due to issues associated with moisture in the airlines. We recommend working with your compressor, manufacturer, or provider for ways to help alleviate those issues. Then that third power source that's available that we can use is hydraulic fluid. We use these often on mobile applications where it's a truck of some sort going down the road, and they could either use 12 or 24 volt DC or hydraulic fluid to power them. There are issues that exist with them. Cold temperatures create some increases in the viscosity of the fluid. It takes longer to circulate through the system and things like that. They can operate much longer than a 12 or 24 volt electric, though. So we find in some of the northern tier states and in Canada, they'll use hydraulic vibrators on their mobile equipment up there because they can run it longer to deal with that frozen muck that maybe they're hauling at that time. So there's two types of vibrators that we're going to discuss today, both rotary and linear, and we'll look at them each a little bit more independently here. Linear vibrators simply are the vibration is obtained by oscillating a mass back and forth within that housing. The force is resultant of the impact or the piston deceleration at the change at the end of each of these strokes. So that's a linear vibrator, and we'll talk about the different kinds. These duplicate a hammer blow, but when applied and installed properly, do not damage the hopper wall. Our objective is to oil can the wall slightly to break the adhesion of the material off the wall. And they're terrific when compressed air is the only power source available and the material is either very dense or has high moisture content. The three types of linear vibrators that we'll look at are continuous impacting, continuous non-impacting, and then single impacting. So to look at the different individual kinds, these continuous impacting, basically, they duplicate that hammer blow the best. The internal piston that is in that sleeve or in that bore travels and accelerates within that. They strike the strike plate on the base and transfer that energy by oil canning the wall into the hopper. This look here with this waveform shows a very triangular, very high amplitude, very high peak waveform. It's due to the impact of at the end of each stroke. These are much louder and less efficient than rotary or the non-impacting vibrators that we'll look at here soon. Next is a continuous non-impacting piston vibrator. This oscillates continuously, but this one does not strike the strike plate. The force results from the negative acceleration of the piston at the end of the stroke. We use these commonly when noise is an issue within a plant, so we don't have that noise of that impact, but the force is resulted from that rapid deceleration at the end of the stroke as it then changes direction. And you can see here on the waveform that it's triangular, but it's got rounded peaks. We use them for wet products that tend to bridge or rat hole, and they're much quieter than the impacting version that we just talked about. Then we have a device that is a single impacting. This one impacts one time on an interval. That interval can be anywhere from once per second up to, say, once every 10 hours, however you want to set that. And what it does is air activates the piston to strike. The airline is evacuated or exhausted so that the piston can reseat and wait for the next activation. These use a controller and a solenoid. That controller can be your PLC or an external controller or timer. And these use significantly less air than continuous versions. So now we'll look at the rotary vibrators that are out there. And you see photos here of electric, and the other three are all powered by compressed air. They operate at a wide range of forces and frequencies, and typically we'll recommend lower frequency, higher amplitude models when dealing with higher moisture content. So that's kind of one differentiation that we use on that frequency of the vibrator. All rotary vibrators are basically some sort of a device with an unbalanced mass that rotates around a center point, resulting in centrifugal force at different frequencies. One of the primary considerations for selecting the size of the vibrator is specific to the application and moisture content or a description of the material. We find that rotary vibration is best applied to drier products that tend to bridge and rat hole. Frequency is important and relates to how often peak amplitude and acceleration occur over time. You can see in the illustration where the high frequency has the peaks very consistent across time, and the low frequency also does, but those peaks are further apart. Amplitude is the physical movement that occurs to a load when force is applied, and we use larger amplitudes for materials with higher moisture content. We talked a lot about the materials, the issues with the that cause the blockages. We talked about some of the devices with the linear and rotary vibrators. Now we're going to go through the steps that we go through for each specific application to ensure properly sized and applied vibrations. We go through these steps here so that we can get familiar with each specific application, and we can address it with what we believe are properly sized and applied vibrators that we at Martin Engineering can stand behind as a solution for your application. So the first step, data collection. We'll talk about each of these a little bit in depth here, but data collection, there's a calculation that we'll do. We'll go through the vibrator selection process. We'll talk about proper location of the vibrator on the structure, proper installation techniques to ensure that we're installing the vibrator correct so that we can move the material effectively and not damage the hopper walls. And then the operation of the vibrators. The data collection part that we do is we use this FlowAid application data form that helps us gather the relevant information that we need, where we can get familiar with the material conditions, the vessel information, dimensions, a description of the problem, the current method of dealing with that issue, and the power availability. Important factors when we get that information, we're looking at wall thickness because that will determine the maximum amount of force that we can apply in any one area. Also discussed in another slide. Worst case scenario, rain, snow, temperature, humidity. We have plants that will run all summer long with no problems, but it's only during those worst case scenarios that they have the vibration in place ready to deal with those issues as they arrive. Very critical. We get a lot of information about the dimensions and whatnot, and it's a totally different solution if the vibrator is to be vibrating a full volume of a cone or slope section of a hopper, as opposed to just cleaning out the residual material that's left behind, maybe in the corners after discharging. And then how will the vibrator be operated? We'll want to know that. Is it going to be automated? Is it going to be operated manually with some sort of a push button switch or hand valve for compressed air powered vibrators? Those things are all things that are very important to understand as we're going through this process. The calculation part, once we've taken that information from that FlowAid application data form, we go to the calculation part. We're going to calculate what we're trying to do is just calculate the volume of the sloped portion of the bin. Critical to know that. We ask on the application data form for the height of any vertical wall, though we really don't take that into consideration. We're looking at either the cone or the slope portion of any bin or hopper. We just want to know we're going to calculate out what that volume is. We're going to multiply the volume by the weight per cubic foot of the material. That way we have understanding of what the total weight in the slope section is of that material. The rule of thumb, and it's a rule of thumb, there are some variations, but we divide that total weight by 10 to arrive at the amount of centrifugal force required to move that material. And then the total weight will determine the proper vibrator in terms of force output. We're going to do a sizing exercise here on calculating a force output. I just made these numbers up. They fit pretty nicely in a scenario, but we're just going to look at this and figure out why we would arrive at this solution. In this case, the wall thickness is 1/4 inch. The width and length of this square hopper is 8 by 8 with a slope height of 5 feet. And the discharge is 1 foot by 1 foot with a material weight of 90 pounds per cubic foot. Our total volume with those dimensions is 163 cubic feet times that 90 pounds of material weight, cubic feet. Our total weight is just over 14,000 pounds of material. Dividing that by 10, our force output needed tells us around 1,460 force pounds is what we would recommend for that application. Here's some of the selection guidelines that we look at though. In that case, we needed 1,460 force pounds. So we're good here on the 5,000 pound max that we would ever recommend to put on one area of any bin or location. The wall thickness determines the max force that we can apply in any one area also. In this case, I highlighted the 1/4 inch wall thickness. We can apply up to 2,500 pounds of force in that area, and we're well within that at 1,460 force pounds. And we would use 3,600 RPM vibrators for drier materials and 1,800 RPM vibrators for a slower speed, higher amplitude force. Given what we just talked about, we didn't really talk about what the material was, its moisture content, but in this case, we determined we needed 1,462 force pounds. Our model MC362510 set at the factory at 60% of max force equals 1,500 force pounds. I feel this would work right out of the box, but it also has up to 2,510 force pounds capability. So if we determined we needed more force, a simple 5 to 10 minute mechanical adjustment of the eccentric weights on that unit will increase or decrease the force output of that unit. One of the 6 shuns is the location. Location matters on where we're going to put these devices. The standard rule of thumb, and again, rules of thumb, there's deviations from it. Sometimes it's based on available area to mount. There could be barriers or restrictions or stiffeners or other things in place. Ideally, if you look at the lower left where the number 1 is shown, that is 1/4 of the slope length up from the discharge. The vast majority of applications we work with, we apply one vibrator, properly sized and applied to move material. That's typically where we want to have that vibrator installed. In some cases, we might have to recommend 2 or 3 or more. It's rare, but sometimes. And one of the scenarios would be a thinner wall than what the force output requirement would be. We'll split that force up and use 2 vibrators. As you'll see, number 2 there is on the opposite wall, a third of the way up the slope. And in those rare instances, we'll go halfway up the slope with other vibrators mounted on the other available sides of the structure. So location matters on this so that we can effectively move the material. The installation's critical here. It's critical for moving material in the most efficient manner, as well as protecting the vessel or the structure that we're mounted to, particularly for rotary vibrators, because we talked about how the linear vibrators, we actually want some wall flex, oil canning, if you will. In the rotary vibrators, we want them absolutely as rigid as possible. We do not want flexing of the wall with rotary vibrators, particularly electrics. And the reason is an electric vibrator is flexing on the wall. That vibrator is wallowing, fighting itself to get up to speed. That increases amp draws. That increases internal temperatures. Properly sized overloads will trip that vibrator out before it burns it up. But we want it rigid, just like any other electric motor you would have in your facility. You want it rigidly mounted. This illustration that you see here comes from the appendix in our manual for our electric vibrators. And what I wanted to point out was a couple things. The table towards the bottom that shows the maximum force of the vibrator, what we recommend for minimum wall thickness with those, and then channel length and channel size and weight. So for instance, for a 1,300 force pound unit, we would recommend a C channel of 4 inches wide by 36 to 40 inches long. We want a pretty substantial length of channel. Sometimes people will ask, how long should I make the channel? I'd say as long as you can make it, it's fine. As long as we've sized the vibrator appropriately for the material that we're working with. And as you can see in the 4-bolt mounting illustration, what this is indicating is we always want the shaft of that electric vibrator to be mounted 90 degrees to the length of the channel, as opposed to in line with the channel. We want the forces as they're rotating to go along the length of the channel, if that makes sense. The channels we provide when we sell vibrators and put them in the field, the channel that we manufacture that are engineered for each of those force outputs are oriented so that the vibrator can only be mounted 90 degrees to the length of the channel and can only be stitch welded. Here's a photo of An electric vibrator mounted on our channel on a pretty thin wall, well, a decent sized wall there, but you can see it's stitch welded in place, and the vibrator shaft line is 90 degrees to that length of channel. We talked about the linear vibrators should be mounted so that we can flex the wall. We use shorter mounting channels. We don't want to mount them right to the wall of the hopper though. Um, we want some reinforcement, but we want that channel to be shorter so we can then flex the wall. Wall thickness is critical. If we're going to use linear vibrators, we might use a number of smaller ones based on thinner walls. And a critical thing about linear vibrators, almost all of them, not all, but almost all of them require a lubricated air line. So here's a couple photos I've got. This one on the left, it's mounted, I don't like the fact that it doesn't have all the bolts in it, neither on the top cap nor on the mount. It's mounted right to the thinner wall. I wouldn't ever recommend that. The one on the right you can see is mounted so that it's on a shorter channel that can oil can that wall ever so slightly. That's also that's a 3-inch piston vibrator, also missing a bolt. But we use that size vibrator also to unload rail cars to give you a perspective as to the forces and frequencies that unit provides. So we talked about all of the shuns, the collection of the information, calculation, selection, location, installation, and now operation. Packing of material can absolutely occur, and it can actually occur when discharging, but absolutely we do not want to run unless we're discharging material, right? Otherwise, you do have the packing of the material. And never run a vibrator on an empty bin. Just talked to a guy yesterday who had some issues with the vibrator tripping out often. And what we found was even though rigidly mounted, when there's no resistance on the other side of the wall, that the vibrator basically is then overforced for an empty void within that and increase the amp draw and kept tripping it out. These next slides, we're just going to look at a few applications where vibrators are mounted with a small discussion as to how they were used. This one's a coal hopper. Hopefully you can see it there. It's a brand new application. That's our channel mount that's mounted there, engineered from a length and width standpoint for the forces that unit produces. They mounted them near all four corners of this large coal hopper to influence the flow that was always seemed to be restricted or clung to the four corners. So the solution here was simply our model MCS, which is a single phase 115 volt vibrator at 2,510 force pounds on our channel mount kit with a safety cable. You can see the cable tethering that vibrator in the event that it would fall off of that mount. Proper operation would be run that for an hour or two upon initial installation, then retorque the bolts, and we should be just fine. Here's a glass cullet hopper. Very irregular shape of the material would cause the material to bridge over the discharge. Install the electric vibrator to operate when the flow detector indicated a low flow situation. There's the model that we use on our channel with the safety cable kit. Here's a wrap bin in an asphalt plant. During the warm months of the summer, that gunk sticks to each other, sticks to the walls, everything. We installed a very high force output, slower speed 1800 RPM electric vibrator on a beam. As you can see, that's a long beam. We got a lot of force going, and that eliminated the issue, and they only draw upon it when they need to. Here's a photo of a single impacting thumper that was set up on a 1 minute interval, solved the flow, and due to the low air volume required to operate this thumper device, it did not consume already limited compressed air capacity. One thump takes very little air. And that's our T300. That's a 3-inch piston vibrator. Here is my contact info. That application data form can be found on our website. Reach out to me with any questions you may have. I'm glad to help. That's what we do. And again, I think it's just critical that the properly sized and applied vibration aspect to this really is something that we can stand behind, because it's critical. We don't throw some vibratory device at applications and hope that they work. You can cause more damage by doing that than helping. Reach out if we can help you. Thank you.